talks are sponsored by the Data Institute, which is the umbrella organization for all data science and data engineering, programming and research that happens here at the university. And what better way to kick off this series in 2026 than with one of our favorite faculty members, Nathaniel Stevens. Yeah. He is an associate professor in the Department of Statistics and Actuarial Science at the University of Waterloo. But before that, he started here. So this is where we like to say, did you start here?
I did.
Yeah, see? So we really built him from the ground. But anyway, so Nathaniel's work sits at the intersection of data science, experimental design, and real-world applications. Today you'll be speaking about online experiments on networks, where traditional A/B testing assumptions break down, and sharing recent research on modeling network effects and improving experimental design in these complex settings. As I said, it is an honor and a privilege to be in your presence, all of you as students, but also Nathaniel's. We are so excited that you're here, and so with that, I turn it over to you.
Thank you. All right. Can everybody hear me? Yes. All right. Well, yes, thank you, Liz, for that intro. I do genuinely, we know that this doesn't always work. Let's try that. How about, okay. Yeah, I do genuinely feel like USF kind of gave me my start, and I do feel indebted to everyone here for that, so thank you. Okay, so we're going to talk about network experiments today. We're going to talk about some specific research that I've done with collaborators at the University of Waterloo, but also try to give you a more broad overview of this problem generally, in addition to talking about some specific research. I will acknowledge just at the outset that this is joint work with two collaborators. So Stefan is a colleague of mine at the University of Waterloo. Trang was our PhD student for a number of years. She's now just 3 weeks ago started as an assistant professor herself at the University of Saskatchewan. And so the work that I'm going to talk with you about today was sort of born out of the thesis work that she did in her PhD. If you want to read more, there are so far 2 published papers on it. I'm happy to share them with anyone who is interested. But just to give you a sense of where we're headed, as Liz said, we're going to talk about online experiments, so I want to make sure that everyone's comfortable with that context to begin with, and then talks more specifically about this network interference problem, and then we'll sort of formalize that problem mathematically and then talk about both design and analysis considerations of experiments when you're thinking of doing this in the presence of a network. Okay, so I know that most of the students in the room know what online controlled experiments are, so if only to refresh their memory, or those of you in the audience who are not familiar with this, I just want to quickly explain the context that we're playing in. So I'm sure everyone's comfortable with the scientific method, the idea of we shouldn't trust something until we've observed evidence to suggest that that something is true. This notion of being skeptical and empirical is sort of the backbone of science. And the backbone of the scientific method are controlled experiments. And that is how, for many, many decades, we, through social sciences, physical sciences, medical sciences, have really made progress as humanity. But it turns out that these experiments are also useful in business contexts, and particularly down here in the Bay Area, in this whole tech world, online controlled experiments are very widely used for optimizing customer experience, optimizing products, optimizing revenue, these kinds of things. So I think the most kind of like canonical A/B test is something like a color change on a website, like a header or a button or something like that. But the idea more broadly is you make some change to a digital product in some way, and you want to measure the effect of that change. That's the whole goal. And there exist many more complicated types of experiments than the colloquial A/B test, but at its basic form, an A/B test has got 2 different conditions that you are comparing. in this experimentally controlled way, and you're trying to determine among those two options which one is best. So you can just kind of keep this picture in the back of your mind. These are the kinds of things that we're experimenting. And just to give you a sense of the scale of all of this, these experiments are happening everywhere in the tech industry. It's harder to find companies not doing this than it is to find companies that are. And it's really kind of born out of this idea of like survival of the fittest. If a company wants to remain competitive and all of their competitors are optimizing through these kinds of experiments, then it's gotten everybody on board. So much so that if you've been on the internet today, you have been a subject or a unit in one of these experiments. Big tech companies are running tens of thousands of these every year, engaging millions of users. Some companies are running hundreds to thousands at any given moment of time. So yeah, just really, really big business and really big area of opportunity. Just another sort of figure there is there exist now lots of other companies who exist solely to help other companies run their experiments. So it is a very, very big business. To give you a sense of some of the sort of dollar values behind this, Google had an experiment a number of years ago where they experimented with the color of the URL in search results. The ones that were ads, they changed the color of blue on those URLs, and it turned out that there was a specific blue that, when used, increased annual revenue by 200 million. Bing also changed the way they displayed ad headlines. That changed their revenue by 100 million. Amazon moved the promotion of credit cards from the home page to the checkout page. That increased profits by tens of millions. Optimizely, one of these companies who helps other companies run their experiments, they are helping these companies on the order of hundreds of millions of dollars. Netflix, in the span of 6 years, grew from being in 2 countries to over 190, and they credit that growth and that success by adopting a culture of experimentation. Okay, so that's sort of the context, and it turns out there's a lot of interesting problems in this context. Experiments, as I said, have been done for 100 years. A lot of the statistical methods were developed in the context of doing controlled experiments in agriculture, maximizing crop yield in a cornfield, or optimizing manufacturing processes, and making widgets in a factory, and you want to make that as optimally as possible. A lot of the statistical methods were developed in those contexts. And while controlled experiments are still useful in tech, there are nuances in the tech industry, particularly with these online controlled experiments, that necessitate new methods or adaptations of existing methods. And so this is a nice paper from a couple years ago that brought together leaders from a number of prominent tech organizations to sort of communicate what are the common problems that all of these companies face. Despite having different products, different users, different goals, they all run these kinds of experiments and have the same underlying statistical issues. So this was a nice paper that sort of explained in non-technical manners what those problems are. And then more recently, myself and some other co-authors from Airbnb and NC State wrote sort of a follow-on paper to introduce these ideas and these problems to a statistical community. So this one is a more technical treatment of those problems. And one of the main problems that comes up regularly is this issue of network interference. And so while there's a number of prominent problems discussed in this paper, the context of the talk is this network problem in particular. But all of this is to say, it turns out that it's an important problem. This particular paper, it's only been out for, I guess, almost not like a year and a half. It's been accessed over 26,000 times. It's the 12th most downloaded paper in this journal ever. And so it just gives you a sense of the importance of this and the interest that exists in these topics. Okay, so that's the context. Let's talk about networks. How does this complicate things? So suppose that you want to run an experiment. You have some new feature, some change you want to make to your product, and you want to test out if that's a good idea. Is it something that's actually going to be meaningfully beneficial? The wrinkle, though, now is what if all of the experimental units that you would engage in this experiment, what if they are connected in some way? And the most, I think, salient example is if they're connected to each other via some kind of a network, like a social network. So think of LinkedIn, think of Facebook, Instagram, X, I guess it's not Twitter anymore. You know, these kinds of things, where there is a network structure and there's, in some meaningful way, connections between all of these different people. And so in a case like that, when you have connections, you can't treat all of these different units as independent from each other. You know, if you look at people in this graph, the ones that have lots of connections coming from them, they are likely to be more influenced by their peers than, say, someone at the edge of the graph who doesn't have a lot of connections. And so when we run an experiment, ultimately what we want to do is measure the impact of that experiment on every single one of these units. The problem is it's harder now to tell what is the effect of the experiment. We can't, the problem is that we'd like to isolate the effect of the experiment from the potential influence that you're seeing from peers in the network. And so ordinarily what we assume in experimental design is that if I'm a unit in an experiment, my behavior, my outcomes, things that are observed about me depend only on the fact that I was put into, say, treatment and not control. But now in a setting like this, I might be influenced by the people around me, the treatment assignment of those people, the outcomes of those people. It's a much more complicated scenario. And so there's this thing in statistics called the stable unit treatment value assumption. It's abbreviated as SUTVA. And so what SUTVA states is that my outcome should depend only on my treatment assignment and nothing else. And as we just said, that kind of assumption tends to be violated in the context of network experiments. And we need to handle that. We need to consider that when we're doing the design and analysis of experiments. We can't just ignore it, because as we'll talk about, it will very much confuse our results. So let's consider a more salient example here. So I'm sure you've seen on the various social networks you frequent this people you may know feature, right? It's the social network basically trying to close triangles. Like there are two people who are connected and they are each connected to someone else that you are not connected to, and they're making recommendations for new potential connections. And it's not uncommon for the LinkedIns, the Facebooks of the world to experiment with the recommendation algorithm that underlies these kinds of recommendations. And so let's talk about how this can be a problem in a network setting. So suppose you have a new version of this recommendation algorithm and you just want to know which one is more effective. Is this new thing we developed better than what we're currently using? That's kind of like the key question. And suppose a feature like this, the way you quantify whether it's successful is, are people using it? Are people generating additional friend requests? And so what you would typically do is, show some people the old version of the people you may know feature, and some people get the new one. And then maybe you track how many friend requests each is initiated, right? The problem though is that the number of friend requests I initiate might be due in part to which version of the algorithm I've been subjected to, but it also might depend on what's going on around me in my sort of network ecosystem. So you can imagine that, let's say the new feature is great, and it really is promoting like really high quality recommendations, and it is generating a lot more friend requests that people are saying. Now let's suppose that I am in the control group, so I'm seeing the inferior version of this feature, and yet maybe friends of mine are in the better version, and I see that they're making all these fun new connections, and I'm like, oh, well, maybe I should invite some people too. Or maybe I'm on the receiving end of a bunch of invites of people who are getting the better version of the feature, in which case I start to reciprocate, and I start initiating more friends. And so now there's this confusion. I am, in some sense, not like a true control anymore, right? Like I am being impacted by what's going on around me. And we can't lose sight of that. We can't just ignore that. And so keep this context in the back of your head. It's these kinds of things where the way I behave and what I do doesn't depend only on the treatment I've received, but it also depends on the treatment assignment of the people around me and the behaviors that they're exhibiting. It just is a lot more complicated. And so this will give you kind of like a little toy visualization of this idea. Imagine we've got a network, and a network we're going to represent mathematically as a graph, and that graph has nodes and edges. So a node is a person, and then edges between them signify some version of a relationship. And let's say that this is colored black and white in terms of like treatment versus control. And, see my cursor? Yes. Okay, so on the left-hand side, let's say white is control and black is treatment. This person is technically assigned a control, but the majority of their neighbors are treated. So they might behave something more like, I don't know, a gray unit, like somewhere between a true treated and controlled user. Similarly, this one up in the top right, their only connection is a treated user. So, I don't know, maybe they behave a little more like a treated user than a controlled user. So the takeaway is that things are not so black and white. There's this kind of gray area where we cannot just kind of think of treatment and control as being completely isolated and independent. The network is sort of breaking that. And so the SUTVA assumption is being violated. And so importantly then, we need to recognize that SUTVA is violated and we need to adapt. And we can adapt in one of two ways. We can either amend the way we design the experiment to acknowledge this network effect, and or we could think about analyzing the experiment differently to acknowledge this network effect. So that's where we're headed. Any questions before we keep going about the context? Super clear, or no one's paying any attention?
Very clear, very clear.
I appreciate it, thank you. You've had to say it. Okay, so the problem. Let's put some math down. Make sure we're all sort of understanding notation that we're about to use. So we're going to imagine capital N is the total number of experimental units that we are experimenting with, and we're imagining now that they exist in the context of some network. And so one way of encoding the information of the network, and hence the graph, is through something called an adjacency matrix. So if we have n units, this thing is an n by n matrix, and the elements encode information about relationships. So any pair, like your ijth entry of the matrix, says something about the relationship between the units I and j. We make a simplifying assumption here that these elements are going to be binary, basically just denoting the presence or absence of an edge. But we can handle much more complicated scenarios. We could handle the direction of a connection, like you'll see here, we're assuming the matrix is symmetric, which basically says we don't care about the direction of the relationship, we just want to know, is there one? But you could imagine something like, I don't know, on X, like you could follow someone who doesn't follow you back, so there could be information encoded in terms of direction. It also doesn't have to be binary, like these could be edge weights that are some numeric quantification of the strength of a relationship. It could be like, a correlation coefficient, something like that is another measuring strength of the relationship between units. So anyway, in what we're about to talk through, we're making the simplifying assumption that this is a binary matrix and it's a symmetric matrix, but we can handle basically anything. The one other assumption here is that a diagonal of that matrix is all zeros. We don't allow for self-loops. It doesn't really make sense to talk about someone being connected to themselves, so we make that assumption. Okay, so that's kind of how the network is encoded, and then on every single unit we have potential other bits of information. The primary bit of information is going to be their response observation Y, that's measuring something about what they're doing. Did they click a button? How long did they spend on the app? How many friend requests did they generate? It's just a quantification of something about that unit. Then we use Z, I guess I should say Z down here, Z to denote the treatment assignment. It's a binary indicator to either treatment or control. So ones are going to be treated, zero is going to be controlled. And then ultimately what we are interested in is the global treatment effect. So there's a bunch of symbols, but essentially what this means is what would we have observed if the entire network was treated what would we have observed if the entire network was controlled, and then what is the difference between them? So this global treatment effect is sort of, on average, what's the difference between those two scenarios? And usually, the way we estimate a treatment effect like that is by looking at a very simple difference in means. If we're treating some units and controlling some units, we just look at their responses and just take the average difference between those two groups. The problem now, in this scenario where SUTVA is violated, is that this estimator is no longer unbiased for the true underlying treatment. You can show that because of network interference, if we take the expected value of GTE hat, you don't get back original GTE. There's complications due to the network interference. So we can't just use something simple like this. We would be, because of the existence of bias, we would be confused in our conclusions. So we need to do something else. And there's sort of two broad categories of solutions here. One is essentially to alter the design so that you eliminate the network interference, and that would allow you to use our naive difference in means estimator. And so these tend to be non-parametric in nature. We're not assuming any kind of model. They are based on versions of clustering often. So graph cluster randomization would say, let's partition the network into a bunch of disjoint subgraphs and then assign treatment at the cluster level. That way everybody in the same cluster gets the same treatment, and anyone around you has, or at least most of the people around you, have the same treatment assignment. So we're really mitigating network interference. And with that out of the way, we can just go back to a difference in means estimator that ignores network interference. Switchback experiments, actually, I should have put this in a different order. Let's talk about ego clustering first. So ego clustering was developed by LinkedIn. It is an alternative to graph cluster randomization, where if you just let a clustering algorithm loose on a gigantic network, it's gonna come back with reasonably large clusters. And if we're talking about doing randomization at the cluster level, that means that there aren't a lot of independent entities that are like treated versus controlled. So you end up having very low power. And so what LinkedIn said was like, well, what if we just did a larger number of clusters, a lot more but smaller, and then still do the treatment assignment at the cluster level, but because we have many more small clusters, we're not sacrificing power in the same. And so that's what they've done. This ego clustering, there's been a couple iterations of it now, but basically they'll randomly select users, and those users are called the egos. They're like the center, and then you look at all the nodes that ego is connected to directly, and that little neighborhood is a neighborhood of what are called alters. And then the ego clusters are the ego plus some subset of the alters. And like the interesting math and computation that they've developed is like, how do you pick, like, if me and Liz are two egos, there's gonna be a lot of alters in common. So how do we decide, which ones are gonna be my alters and which ones are gonna be Liz's alters? So there's this kind of like pruning of alters, filtering of alters. And so they've got some pretty interesting stuff looking at like how to do that in a way that is both computationally efficient, not wasteful, like you don't want to throw out information, and you want to make sure that what you're left over with is something that is giving you like valid statistical inputs. So anyway, that is an interesting alternative to traditional graph clustering randomization, which came out of Facebook. An alternative is a switchback thing, where typically the way that works is you just turn treatment on and off and sort of altering that at random through time. So like today everybody's treated, tomorrow everyone's controlled, the next day everyone's controlled, the next day everyone's treated, and just kind of randomly flip back and forth between those. And again, what that achieves is you've, on any given day, eliminated the possibility of a network interference because everybody has the same treatment. But in all cases of what we've just talked through here, we are sacrificing power. We are, by one mechanism or another, kind of throwing out some information. At any time you don't do randomization at the unit level, you are sacrificing power. So the other family of methods that are meant to handle this are model-based methods, parametric ones that say, what if instead of altering the design of the experiment to eliminate network effects. What if we tried to model those network effects? Because if we could do that, then we could analyze every single unit, and we could try to capture the network interference. We could try to capture the treatment effect. And so there's been quite a bit of work done into like defining statistical models that do this effect. And they vary in, did I lose this? Yeah, there's a. Okay. So there's a couple different kind of like frameworks for thinking about developing models, like how to model network interference. And think about like an ordinary linear regression. You have kind of two components there. There's the mean component, like your x's and your betas, and then there's a variance component. And so there has been proposals to model the network interference in both sides of that, either through basically the covariates and the mean component of the model, and also alternatively through the variance structure. And as I said, the benefit of these is that they stand to be more powerful because we're analyzing every single unit, we're not throwing anybody away. Randomization can still happen at the unit level. So all of that sounds great, except that all models are wrong. Some are just more useful than others. That's not my quote, George Bach said that. But it's, I think, more prevalent here and more apparent here than in many scenarios because network interference is a very hard thing to model. So if you're assuming a model and you're getting it wrong, then essentially everything you're doing is useless. And yet, there are still models being proposed that are effective, but it is something you have to keep in the back. So we're going to focus here, though. The development that we've done is model-based, and so that's what I'm going to explain in the next remaining. Okay, so one such model is this thing that we call general additive network effect model. So let's talk about what that is. That's it. It looks like a regression. So it's the kind of the structure is my response is influenced by a couple different things. One is this like constant mu, it's like an intercept term. It says something like what is the baseline outcome. Then tau, the coefficient on our treatment indicator Z, is the direct effect of treatment. So think about ordinary regression coefficient interpretations. We say like holding all else fixed, what happens to my response if I increase this x by 1? So in this case, that x is z, we're going from 0 to 1, like what happens between control and treatment. So the tau gets at what is the direct effect of the treatment, holding all else fixed. So if the network was all the same, and for this particular unit, what is the difference between if that unit was treated versus control? So that's tau. And then we have these two other terms that are meant to model out the network interference. And you can see there that they're written very generally, and that's kind of on purpose. There are some restrictions that we'll talk about in a minute, but the idea is that it's meant to be intentionally flexible to accommodate different structures of network interference. So these F functions are parameterized by eta. So eta can be some parameters, it can be a single parameter, it can be many parameters, or it depends on the functional form of these Fs. The Fs, as you can see, also have different subscripts, so like the way your treated neighbors influence you might not be the same as the way your controlled neighbors do. So we're allowing for heterogeneity in that respect. And then there's also data that might be encapsulated there. So the data could be things like, this sort of matrix combination of the adjacency matrix, so it's representing information about the network, the treatment assignment vector Z, response vector Y, there could be other covariates X. So this sort of framework just flexibly accommodates all of these things in a manner that is meant to help explain variation in our response. And then of course, the model's not going to be right, so we have this error term. I think I basically said at that last point, like this is super general on purpose. It's meant to be very flexible. But so it's easy to write something like this down and be like, oh, wouldn't it be great if we could do this super flexible thing? Well, it turns out we did. We can, under certain regularity conditions, handle almost any functional form for these Fs, and therefore accommodate a a lot of realistic scenarios. Before talking about anything too specific, I'll just acknowledge that this general framework kind of encapsulates as special cases a bunch of other models that already existed out in the literature. So just kind of explaining a couple of these. Imagine if there were no Fs, like we go back here. Imagine those two yellow F terms, there was just nothing there. In this case, there's no network interference. That is basically what SUTVA assumes. So we call that kind of baseline model the SUTVA one that ignores network interference. The next most basic version of the model is to take those two functionals, like the FT and the FC, to basically just add up how many treated neighbors do I have, how many control neighbors do I have. So that would turn this expression into an ordinary linear regression with 3 covariates. One covariate is treatment assignment, the other covariate is simply how many of my neighbors are treated, and the third covariate is how many of my neighbors are controlled. Very straightforward, very easy to fit as an ordinary least squares regression, but also maybe a little too simple. Then there's something called the local aggregate model, that's what the LAG stands for, and that functions very much like this linear network effect model, but instead of just counting how many treated and controlled neighbors we have, what this does is it asks what is essentially the average response of my treated and controlled neighbors. So it's more of like an autoregressive, like a spatially autoregressive model in that respect. The homophily model is sort of a combination of the previous two, and then one that we've proposed, like a particular specification of these GANE models, is this power degree model, where you can see the only difference in this row from the second row is that we've taken that count of like number of treated and controlled neighbors and raised it to some power lambda. And the idea there, I'll say more about it in a second. So anyway, what I'll stop with here is just to say that there existed lots of other models, and what we've done here kind of unifies things. And so these are just sort of the virtues of it. Like it's interpretable, it's flexible. It allows us to estimate and interpret any kind of causal quantity you might care about, things like your treatment effects, your network effects. We have shown that you can use maximum likelihood or sometimes quasi-maximum likelihood to get the parameter estimates in a very flexible way that permits confidence intervals, hypothesis testing, all kinds of ordinary likelihood-based goodness of fit testing, like all of the stuff you would want it to do, we made it work. So that's been quite helpful practically. So what I want to talk about though is a specific specification, that power degree or POWDEG model. And basically what it does is it takes that linear network effect model. It says, I'm going to be influenced by how many of my friends are treated and how many of my friends are controlled. That makes sense, that I would be influenced by that. But what the linear network effect assumes is that the influence from my peers grows linear. Like the influence of my second friend is the same as my 1000th friend. And that feels like maybe a strong assumption, that probably there would be some tempering, as the more and more friends you get, the less and less influence they have. Like you really enjoy your first slice of pizza, the 9th is maybe less enjoyable. Like that kind of diminishing return type relationship is what we are sort of hypothesizing with a model with this structure. And so these lambdas are a parameter that you would estimate from the data. So you don't have to go in assuming you know what the nature of that relationship looks like. It is just now a nonlinear regression, and we can estimate all these parameters effectively. And so when we have these gammas, and those gammas are sort of quantifying the nature of the relationship from your peers. So it turns out that this was a model that worked reasonably well, and that's what I'm going to try to convince you of in the next couple slides. The one nice thing, and another nice thing about model-based inference is that quantities like this global treatment effect that we care about, we can just write it down directly in terms of model parameters. It was just an expectation. Expectation if everybody was treated versus expectation when everyone's controlled. We can work that out in terms of these model parameters. And so once we've got our likelihood estimates, we just plug that in and we've got an estimate of GTE. We can do delta method type magic and get hypothesis tests, confidence intervals, all that kind of stuff. Including hypotheses of this form. So we might care about something like, is that direct treatment effect tau equal to 0? And that is, importantly, a different question of what is the global treatment effect. Because the global treatment effect is a more holistic thing, like what happens when the whole network is treated versus controlled. So those are two hypotheses of interest. But then we might also test hypotheses about the network effects. In particular, are there any? The second null hypothesis essentially asks, is SUTVA right, or is SUTVA wrong? Are we violating the network interference assumption? And then supposing that we do, then we could ask questions like hypothesis 3, is the influence from treated versus control neighbors the same? So there's any number of hypotheses you could work out here based on the parameters, but those are four that seem to have interpretable value. So I want to, through simulation, just kind of show you that this works the way we want it to, and therefore is a sensible thing to do. The context is a reasonably small network. It's a Facebook network of Caltech students. There's 770 students, so that's all the little yellow nodes. And then there are a little over 16,000 connections a month. So that's our network. And then what we do in the simulation is randomly assign them a treatment control. So just like a Bernoulli coin flip is determining that at random. And then we're simulating response observations from that POW-DEG model according to specific parameter values. And so what I'm going to show you is that when we do that, say, 1 million times, and then estimate the parameters, we are able to estimate them the way you'd like to. So these are histograms of running this many, many times and constructing histograms of all of the estimates. So the fact that they are all centered at the true value is nice. It suggests unbiased estimation. The fact that they're all sort of like bell-shaped symmetric around that suggests that the asymptotic normality that we proved should exist does hold in finite settings. And this is a very finite setting, like only 770 nodes, and we're still seeing kind of the asymptotics kick in. And then just a couple other comments. You see that basically the different coloring is based on a couple different values of the lambda. And you can see that essentially what that impacts is how precisely we can estimate some of these parameters. Although the tau is not impacted by the lambda, which makes sense because the tau is asking like what is the direct effect of treatment, ignoring anything to do with the network. So it shouldn't be impacted by the lambda. But everything else tends to be estimated more precisely with bigger, if lambda is truly bigger. But remember, lambda itself is a parameter, and that bottom middle plot shows our ability to estimate that. So anyway, the key takeaway from this is that this methodology does a good job of estimating the parameters and in a way that feels familiar. The other thing, though, I'll acknowledge is we're kind of cheating here, right? Like we are using the model to generate the data, and then we fit that data with the same model. So like, it would be pretty terrible if these looked bad. But they look good, so it's like a step in the right direction. And we'll, in a minute, talk about, well, what happens if you generate with different data, with different models, how does this one handle? But before that, I want to show you this plot. I think the only thing that I really need you to kind of focus in on is, in any given panel, there is pretty good agreement between the pink lines and the blue ones. And what those are comparing are asymptotic variances versus empirical variances. So the asymptotics give us basically an equation. We can say this is an estimate of variance. The question is how good an estimate is that? It is relying on asymptotic normal theory. And we're talking about 770 nodes. That's not infinity. So how good agreement do we get? And I don't remember which is which. The red is the sample one. So we said we did a whole bunch of repetitions of this. We got a whole bunch of parameter estimates. What is the empirical standard deviation of those? That's what the red line is showing. And so we don't get perfect agreement everywhere, but in general we get decent agreement between the theoretical asymptotic result and the empirical one, which basically just says that in practice, when you collect data and you only have one set of data, you can never have that empirical estimate, because to get that, we have to do this many, many, many times. So what this gives us is assurance that with a single set of data, we can use the asymptotic variances and they're going to be trustworthy. We can rely on them. We similarly kind of tested the power of these hypotheses The 4 different hypotheses we mentioned are the 4 different panels, and then essentially on the horizontal axis, we are just increasing the magnitude of the effect that that test is meant to identify. And so these things work the way you want them to. Like, you know, it's when there's 0 effect, we have basically type 1 error rate controlled, but then when there is an actual positive effect, we are increasingly able to identify that as that effect gets bigger. So the hypothesis testing works the way it does. Now, circling back to that issue of like all of that was in some sense in an ideal scenario where we were using the same model to both generate and fit the data. So here was a model specification investigation we did where we considered 5 different models, basically the ones I talked about in that table previously, and we used each of them to generate data, to simulate data, and then we also used each of them to estimate their parameters. So like along a diagonal, you have a model being used to both simulate the data and estimate the data. So that diagonal is kind of like the idealized scenario. But what's more interesting is to look at like row by row, how does a model do when the data came from another model? So the thing I just kind of want to zoom in on in any given panel here is the middle row is our POWDEG thing. And what I'll argue is that it is the only model across these 4 scenarios where it performs well by all these metrics. So the top left metric is basically quantifying bias. So formally, it is the log of the estimated treatment effect over the true treatment effect. But we would like the estimated and true to be basically the same. So we'd like that ratio to be 1, so the log of that we'd like to be 0. And according to the color gradient, that's things like closer to white, show something close to unbiased estimation. And the only model whose row is mostly white-ish is the POWDEG, so that's reassuring. The next top right panel has to do with variance estimation. And the whiter the color, the lower the variance. So you can see SUTVA looks really good. This whole bottom row looks super, super like low variance. But what we're actually observing there is the bias variance trade-off, because SUTVA is really bad in terms of bias. It's a very simple model. So you know from intro ML that you have something super, super simple. It's going to be high bias with low variance. And that's what we're seeing. So SUTVA is not actually good. It just happens to be low variance because it's ignoring network information. But POWDEG remains reasonably non-green. So that's now 2 sort of feathers in its cap. Low bias, low variance. The next bottom left has to do with confidence interval coverage. So like, are we actually able to capture the true GTE in our confidence intervals? And the closer we are to a dark green, the higher the coverage. And many models do okay here. Ours is one of them, so that's also good. And then finally, the bottom right is showing model selection. So using AIC as a model selection criterion, you can see like the diagonal is generally like a darkish green, meaning models are able to kind of pick themselves when it's appropriate to. But the other thing is like this POWDEG row, among other rows, is more green than others, meaning that it often can work well at fitting data, even if it was a different model, true underlying model that generated it. So all that is to say, this whole GANE framework is very flexible, very useful. You have a lot of flexibility to model the network effects however you want. But it turns out this like POWDEG specification in particular it works pretty well. Any questions about this stuff? Because we're thematically going to move on here. Okay, so that's addressing the network interference stuff on the analysis side. Like we basically said, we're just doing Bernoulli coin tosses to do treatment assignment, and then we're going to account for network interference on the analysis side. So next what I want to talk about is how do we think about design if we know that, let's say, the POWDEG model or some version of a GANE model is how we want to analyze the data. And so what we developed is a genetic algorithm-based method for picking designs. It turns out to be very, very flexible and very, very useful in this setting. So sort of give you the overview here. So actually, even before this bullet, so the phrase optimal design comes out of experimental design literature, and the idea behind it is if you know that you're going to analyze your data according to a particular model, you can sort of back calculate through the mathematics, like what is a good design for that intended analysis? Like how do I optimally, in our case, treat versus control based on some objective? So we're going to be optimizing with respect to some objective, and the search space that we're optimizing with respect to are these like treatment assignment vectors. And so the Bayesian or pseudo-Bayesian optimal design that we're going to handle here is sort of handling a couple things. One, maybe the first thing I'll acknowledge is that what we're aiming to minimize, our sort of objective function, is based on minimizing the mean squared error of that treatment effect, the global treatment effect that we care about. We would like to estimate it both accurately and precisely. So minimizing MSE will achieve that. And so ultimately what we're going to do, focus on maybe only on the first argument statement. What we're essentially doing is searching that whole space of possible vectors of ones and zeros of length n. There's a lot of them, 2 to the n. That's the total possible search space. And we're asking ourselves, which of those vectors is optimal from the perspective of minimizing the global treatment effect estimate? Or minimizing the MSE of that estimate. So that's the goal. The problem though, and let me back up for one moment, is if we look at the global treatment effect function here on this slide, you can see it's a function of unknown parameters. And the MSE will also be a function of unknown parameters. So what that means is if we want to think about all these things at the design phase before we've collected any data, we have to give some thought to like, well, what are those parameter values? Much like in a traditional sample size calculation, you're optimizing for power, you know, they have to come up with a guess for the variance, right? You have to plug something into these calculations. And so what we want to move away from is that kind of like strong assumption that you have a good idea of what these parameters are to begin with. And so that's where this Bayesian idea comes from. The Bayesian idea is us saying we probably don't know exactly what these parameter values are, but we might have some sense of like the possible values they might take on. We could define a distribution of possible values for those parameters, and in Bayesian settings we call that the prior. And we are ultimately going to do a frequentist analysis at the end, which is why this is sometimes called pseudo-Bayesian. We're just bringing in the kind of like Bayesian flavor of there's uncertainty before we observe data about what these parameters are. So let's not fool ourselves into thinking we can identify them exactly. Like if we knew these parameter values exactly, we wouldn't run this experiment in the first place. So this whole Bayesian thing is us saying, let's acknowledge the uncertainty in these parameter values. So ultimately what we're optimizing for, this criterion phi, is, you can see it's an integral. It is essentially what is the expected MSE as a function of that prior distribution. It is just an expectation. We implement it, in fact, as an average. We're not doing numeric integration. So you can really just think about it as the average MSE over a bunch of possible parameter values. And so the question then becomes, if this is the thing we want to optimize for, and in particular minimize, how do we efficiently search this space? Because that is a big space to look around in. 2 to the n things for n of typical sizes in these kinds of experiments is just infeasible. And so that's where the genetic algorithm comes in. It's a sort of general purpose meta-heuristic optimization algorithm that when tailored to this context actually works pretty well. So let's talk about what the genetic algorithm is and how we're using it here. So it's sort of essentially, I think it was a computer scientist developed it many years ago just to kind of mimic natural selection. That was sort of the idea. And And so it's sort of nature inspired. It's meant to be like, how do you get from one generation to another in a way that is preserving good traits of the previous generation and maybe weeding out traits that are not so. And so it's efficient, it's simple to understand, it's very flexible, so it's a very good candidate in this context. I already said that, so reverse order. So what we're doing is basically adapting it for use in this context where, you know, the genes, if you will, are the potential design vectors, the Z's, and we're trying to use this algorithm to search through those Z's. And there's specific to this algorithm these mechanisms called selection, crossover, and mutation, and we can manipulate those in a way to try to do this effectively. So let's talk about each of those pieces. So this initializes with some population of candidate designs or candidate genes. The size of that population we'll call NPOP, but you can just imagine this at baseline is like, I don't know, let's say 100 vectors, 100 Z vectors. Those Z vectors are just filled at random with ones and zeros, according to a Bernoulli distribution with probability point approximation. So that's kind of generation 1. Now how do we get generation 2 and any generation thereafter? What we do is we retain some proportion of the original generation that worked well. So from our circumstances, we can look at all of these, let's go back here. We can look at any given design vector Z and plug it into this calculation and ask, like, what is our design criteria? So we can do that for the entire population and say, okay, well, which ones were the best? So we can like rank order them in terms of who minimized or who got this criterion the smallest. And so on that basis, we will preserve some percentage of the best performing designs. They sort of move forward into the next generation. And that percentage is what is called alpha elite. Generally, you want this to be a reasonably small number because, you know, the bigger the number, the less elite candidates you're actually retaining. Then we fill the rest through crossover mutation. So the way crossover works is basically you take two parent genes and they produce a child gene. And so you have some fraction of your previous generation become eligible parents and they mate and produce the next generation. And so a child is created from two parents in our context by basically just randomly mixing the components of their two design vectors. And that's what that says. And then the mutation step is to say, okay, these parents have created a child, let's at random mutate that child. Just, you know, we want to do some bit of exploration and exploitation here. So at random, we're going to mutate a small percentage of these elements. And that's the idea. So that's it in words. Let me show it to you in pictures, because I think pictures will help build intuition. So here, MPOP is 10. Imagine our population initially has got these 10 design vectors. Red versus blue is treatment versus control, and the red versus blue is just assigned at random, okay? So let's suppose that alpha elite is 20%, and so we retain the two best vectors from that generation. So moving into generation 2, we keep those. Now I have to think about how do we backfill these other ones around. So to do that, we come back to generation 1. And let's say alpha parents is 40%, so we'll at random pick 40 or 4 of these vectors to be the eligible parents. And then at random within that, we pick 2 of them to produce offspring. So that's the way that happens is we take these 2 vectors and we do the crossover step. And so you can see row by row in this new vector, whether it's red or blue, is basically making a random choice to inherit that property from either of the parents. And in the case that both parents, like for example here, share a red, then this is guaranteed to be a red. So in some sense, we are just producing offspring in a way that is a random mixing of the 2 parents. But then we're not done. Then we mutate the child. At random, we're just going to sort of delete some entries, and here we're just picking 2. The 20, I can't remember how many I did. 12. we delete what we learned from the parents and then just pick at random. And so you can see in one case, it turns out we swapped, we changed what was inherited from the parents, and then in the other case, we retained it. But that's just like the small mutation that allows us to explore a little bit. Okay, so that vector is now populates generation 2. And so to get the next vector, we have to do it again. Go back to generation 1, who are eligible parents. Maybe we pick these 2 at random, and then we do the crossover, then we mutate, and now that new vector, that is a new vector in generation 2. And then we fill in generation 2 accordingly, and then we do that again and again and again and again, many, many times until we iterate toward a solution. So it feels vaguely like gradient descent, where we have this objective that we are trying to minimize. It is less like gradient descent in the sense that these are very discrete steps that we are taking through the search space. But nevertheless, we are basically asking, how can we improve at any given movement toward an optimum? So that's the idea. Okay, so how well does this work? We compared it to several other ways of constructing designs in a couple different network settings and a couple different model settings. So there's 3 different networks here of different sizes. That middle Caltech one, that's the one you've already seen. We have another Facebook one, that's the U-Michigan one. And then the smaller one is an Enron email exchange network. So you can see that they're varying in size, but we're just using that as sort of providing some diversity in terms of the context of our comparison. And then we're comparing to other ways of deciding who to treat and who to control. So as a baseline, we compare to just naive balanced randomization, that Bernoulli coin flip. How well does that kind of baseline industry standard perform relative to what we're doing? Then there's a version of randomization called restricted randomization, which is essentially still a Bernoulli coin flip, but subject to a couple constraints. And the common constraints imposed are to make sure that you have the same number of treated and controlled neighbors or units in each group, and then also control the degree distribution, so that the degrees of the people who are treated and the degrees of the people who are controlled look the same on average. So it's basically just a restricted randomization or constrained randomization. Then we compare to some cluster randomized approaches, and then also just random search. Random search is the most simple meta-heuristic algorithm where you just at random plug z vectors through this equation. So there's no sense of like learning from past behavior. It's just completely random. And it turns out that it can work well, but it's generally less efficient because it's not very targeted. So we compare to those, and we quantify that comparison on the basis of this kind of efficiency score, where we're comparing the best design by any approach has associated with it the optimized criterion value, and then we compare that to the one that you get when you do the balanced randomization, because that's just like the naive standard. Because smaller is better here, positive numbers are good and negative numbers are bad. And I'll just kind of throw up the results here for a second and just draw your eyes to a few qualitative components of this. So the vertical dashed lines, that's sort of like the reference, that's at 0. And if a box plot is to the right of that line, it's a good thing. If a box plot is to the left of the line, it's a bad thing. The various columns are the different network contexts, and then the different rows are different models. And so what is highlighted then in red is the performance of the genetic algorithm. And what that kind of shows is that, in some sense, no matter the network and no matter the model, it's performing pretty well. It is not, and admittedly, it's not uniformly the best. There are some scenarios where some of the, like down here for this binary time step model, these box plots are a little bit further out to the right than the genetic algorithm one. So it can be outperformed in certain scenarios, but you never see what worked well here. these cluster randomizations, you can see that in other scenarios, they perform abysmally. And so what's nice about the genetic algorithm, as opposed to some of these other things, is these other things are very tailored to specific contexts, whereas the genetic algorithm is really flexible, and it works either very well, or at least mostly well, in essentially every setting. So we kind of advocate for its use when doing these kind of design problems, because it's flexible and adapt to different scenarios, which is unsurprising as natural selection. The other thing we compared to was, we have this Bayesian component which says like we're making, or we don't believe that we know the true parameter values. So instead we're going to submit into this analysis like a potential distribution for those values. But what would have happened if we did instead put in very specific parameter values instead of a prior? And it probably is not worth really explaining how the plot works, but the punchline is that, and it's obvious, it's what you would expect, that if you guess right at those parameter values, then that's the better thing to do. You're going to get a much better design criterion, a much better design, if you guess those parameter values right. If you guess them really wrong, though, then you have a completely useless design. And so what this kind of communicates is that although it's possible to be beaten, this idea of like genetic algorithm plus Bayesian design criterion, it is very protective in a sense that it works well, broadly speaking. It's not going to become completely useless in any kind of scenario. It's just like a really useful and broadly useful workforce. Okay, so to end, I guess the first part was that GANE framework was a flexible and interpretable way to model the results of network experiments. And then sort of backing up a step, the genetic algorithm and Bayesian optimal design is a very good way to do the design of the experiment, knowing that your analysis down the road might be one of those GANE lines. This work is by no means finished. There's a lot of opportunity here. I'll just very quickly talk through a couple of these. So we have, in everything that we've assumed, everything we've done, assumed that the entire network is available, and that like we just know who is going to be in the experiments. We treat everyone, we control everyone. But often that's not how online experiments work, where instead in an online experiment you are doing the randomization as people come into the experiment. So it could be the case that some of the people in your network are in the experiment and some of them aren't. So thinking about how to adapt to that sort of sparsity when you're doing sequential treatment assignment is something we're thinking about. For now, we're just assuming those design vectors are all like red and blue dots. What if there was more colors? What if we had many treatments? We can certainly accommodate it. The math works, but the question is how well does it work and is it worth the time? Everything I've shown you so far assume the response was continuous. What if it's binary? And then also scalability. So this works admittedly quite well and in a time frame that is not prohibitive, on the order of like thousands to tens of thousands. But if we're talking about hundreds of thousands or millions, I need a gigantic computer, or we need to like speed up the genetic algorithm in some way. So we're thinking about how do we scale this to slightly more realistic context. Anyway, I will stop there. Thank you for your Any questions?
So the use of I was a little confused on how we're selecting the best traits in the genetic algorithm to then move on from the parents. So yes, I'm using that on like that.
Yeah, good question. So how, like, what does it mean to be best, especially in this like selection operator? So it all comes down to the evaluation of this design criterion. That's going to be done for every single one of the vectors. And the smaller that number, the better. So when we're picking like which vectors to move on as being like they were the best, well, they're the best in terms of having the smallest phi values. And then similarly for the selection of parents, if you could select parents at random, or you could say, well, I'm going to take the top 50% and then they are eligible parents. We want to in some sense, prioritize what they did well and explore that further in future generations. But it all comes back to this. I appreciate you swaying. I'm not lost. You said I was confused. That made me feel better. Appreciate it. Yeah.
I just have a follow-up on that as well. So is that calculation of phi specific to the experiment you're running, or?
Yeah, good question. So what it is specific to is the model. So let's go back. Okay, so what we're doing is trying to estimate the estimator of this. And we'd like to do that well. And the structure of that quantity is going to change depending on the model you're using to describe the y's. So that phi calculation is very particular to the model that you're using. It's a different calculation for our Powdeg model than it would be for the homophily model. So you do admittedly have to work that out for whatever model you're assuming describes your scenario. But aside from that, it's flexible in the sense that it can accommodate any model. You just have to work the math out. Yeah. But in terms of the design, all of this is assumed we're just doing binary treatment assignments, either treatment or control. So those Z vectors are just the binary ones. So the calculation of the MSE doesn't depend so much on the design because we've a priori sort of assumed that particular scenario. Yeah.
How big were the treatment and control groups in comparison to the networks?
Well, 50-50.
You used all the networks.
Well, yes, and so that was the motivation behind, sorry, I lost my cursor. The motivation behind that one extension that is like the sequential treatment assignment, we've assumed that we are using the whole network. So what happens if, it's the same thing as saying sequential treatment assignment, what if you only had access to a subset of the network? How do you accommodate that?
If you're using like a large network, but only a small percentage, how hard is it to like compute influence based on like distance in the network or something?
Well, exactly. That's I think the key struggle there. Is that if you've got some sub-network, what it means is that you're throwing out information about edges with other nodes that you're effectively ignoring, and so you are going to miss any potential influence those people have on them. Like they can't be treated or controlled because they're not in the experiment, but it doesn't mean that they don't exert some influence. So it's a harder problem, which is why we didn't do it first.
Yeah.
Any other questions? Yep.
Two questions, one conceptual and one very concrete. Conceptually, the original, the start of it, two plots of land, one gets a fertilizer, the other doesn't. It's clear, treatment and control. Isn't that actually a network problem, except the network value is 0? And so it's really a continuum.
Yep.
And I would go further and say that actually network is not 0 in that case, because you have climate that changes. So if you decide that a certain treatment of fertilizer is best, it may only be best in dry seasons, not in wet. And so you're not taking into consideration that. So everything is
Everything's
a network.
a network.
Yeah.
And networks are everywhere.
And then my second one is, if you want to do an experiment to see if an algorithm produces better results, the color blue or a different way of taking people, whatever, can't you just take the entire network as the control and measure that thing currently, and then give everyone the treatment and measure it again, and you have a perfectly good A/B model?
Yep. So excellent questions. I'll answer them in reverse order. So what you just described is the switchback experiment, where everyone on Monday is treated, everyone on control is Tuesday, and they generally don't stop at just 2 days. They will add more days in because maybe Tuesdays and Mondays are inherently different for some other reason. But yes, that is the switchback experiment, or switchback design. Back to your other question, yes, everything is a network. And in fact, the earliest work on this was done in agriculture, in crop fields, where, like, yes, climate, I agree, like that's something that is impacting both plots. But even fertilizer, it's hard to control that it only goes on this one, like it spills over into this one. That's where the term spillover comes from. So people were thinking about this even back in the day at a slightly smaller scale. But you're absolutely right that I think you could observe or regard anything as a network, and you just have to decide if you're acknowledging it's there. And you're right, there is in some sense a continuum that where on the continuum am I at in terms of thinking of this as a network. Yep.
When you're going over the general effectiveness of GANE,
Yep.
is that assuming that you were using the GANE model that you were showing us earlier, or?
Yeah, so I glossed over that very, well, I didn't gloss over, I just didn't tell you it. Every row is a different, this chunk is one model, this chunk is one model, this chunk is another model. So this one is our PowDag one, but then these other ones are other models too, totally independent of our stuff. And we're showing that even if you use somebody else's model, this is still a sensible